Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. This afternoon, we are very lucky to have again Professor Zurab Janelidze with us. As you know, because he presented already in this forum, he's a professor of mathematics at the university in Stellenbosch, in the Department of Mathematical Sciences. And he's at the moment also the president of the South African Mathematical Society. So congratulations for that appointment, Zurab, from all of us. Yeah. Zurab is also a member of the editorial board of some prestigious journals like the Applied Categorical Structures and Cahiers de Topologie et Géométrie Différentielle Catégorique, yeah? And that are some of the most prestigious journals in the field of category theory, which is also his area of research. Yeah? And today he will share with us something about Noetherian information system, which is something that sounds very, very interesting to physicists. Yeah, and obviously also to many other people, because we have quite a mixed audience in Zoom with us today. Yeah. Zurab, you already kindly started sharing your screen, so I will ask you in a second to start your presentation. I just want to remind everybody again that first that you're welcome to ask your questions in the Q&A, and since we are not so many, you're welcome to raise your hand and we can give you the right to speak at the end of the webinar or before the end of the webinar if it is very urgent. And also I would like to invite all of you to join us for our virtual social event in Kumo Space. The link is on the announcement of the talk, and I will post it just now again in the chat. So please join us there for a short social interaction with the speaker. Zurab, please, I've done my adverts. You're welcome to start with your presentation, and thank you very much for being with us this afternoon.
Thank you very much, Francesco. It's really a great pleasure to be able to give this talk. Thanks for the opportunity. And I just want to say that I think NITheCS is doing something fantastic for everyone, and I'm very happy to be part of it. This talk is a kind of attempt to take something that comes from very abstract mathematics and try to think about it in terms of possible applications outside mathematics. It's an idea that came to me when I was preparing my inaugural lecture a couple of years ago, and then I didn't really have much chance to develop this idea further. And for this talk, I tried to do some further development, and the result is what you will see. So let me begin with this video, which probably you'll find it difficult to hear because the sound quality is not very good, but nevertheless, I want to play it.
Let me just show you how to construct the MATS, which is the fun of the lemma anyhow, okay? So you assume you have an element in the kernel of gamma that is an element in C, such that gamma takes you to 0 in C prime. You pull it back to B, like nat G, which is surjective.
Hold it. That's not unique.
Yes, it is unique, Mr. Cooperman, up to an element in the image of F, all right? So we fold it back to a fixed B here. Then you take beta of B, which takes you to 0 in C prime.
So this is a movie from 1980. It stars Jill Clayburgh and Michael Douglas. And in this specific scene, you see something called the Snake Lemma, which is one of the theorems one can prove for certain types of algebraic structures, and more generally in certain types of categories. It has application in homological algebra. That's where it comes from. But then there has been also a lot of interest in this lemma, irrespective of its homological algebraic applications. You see there is a diagram of objects and arrows, and you reason around this diagram to get some more arrows and some conditions coming out from the diagram. And it's just an example of one of many theorems one can establish in abstract algebra and that can also be further generalized and worked out in the context of categories. And among such theorems, some of the first examples of such theorems are so-called Noether isomorphism theorems. And they're called this way because it was Noether who first formulated them in the full generality that she did in her paper in around 1920. It was built out from some ideas in a more concrete scenario of Richard Dedekind. And as everybody knows, Noether played an important role in development of abstract algebra and abstract mathematics in general. And so Noether isomorphism theorems are among those theorems which reoccur a lot in various studies of various different algebraic structures. When you have this supply of theorems that are very general and can fit in different contexts, one wonders whether there is a unified context where you can prove these theorems once and then just apply in all the special cases instead of having to reprove it in every different special case. And these kinds of questions of finding a unified setting for proving such theorems came up already during Noether's time. Already Noether wanted something like that. But then with the development of category theory, it was fully possible to realize it. And so there have been a lot of various different contexts in category theory where one can prove these things in a uniform way. And this is basically the background of mathematics on which the present talk builds. So I'm going to stop there with the introduction, and I'm going to jump directly into the content of the talk. And then at the end of the talk, we're going to come back a bit to history and relating these things to things that are well known. So the first section of the talk, the first part of the talk, by the way, these slides, they're actually not slides. This is actually a post on my blog, and you can view them also in parallel if you want to, and you can scroll down in your own pace. I'm going to copy paste this in the chat in case you want to do that. And the other thing I want to say is that if at any time you have a question, feel free, please, to interrupt and ask. Okay, so the first concept that I'm going to introduce here is a concept of an information system. Now, I don't know much about information theory, and this concept I'm going to introduce is probably not very far from existing concepts, but it's a fresh take on this thing. And also information system, in the sense that I'm going to define, is going to be something very abstract. It's not going to be as concrete as perhaps in information theory one would want to have, but the idea then would be to try to make it more concrete in the future. So let's begin with the notion of a network, which is nothing other than a graph in the sense of category theory. So this would be a collection of nodes, which we can call devices for the sake of this terminology. And then there are channels connecting these devices, and you can have multiple channels going from between the same two devices and also in opposite directions. So the channels are supposed to have directions. So it could look something like this. There could also be devices that are isolated from the rest of the group. So something like this we're going to call a network. And as I said before, in category theory, this is called a graph. And I'm actually going to be adapting slightly usual category theoretic terminology to make concepts a bit more intuitive for someone who might not have encountered category theory before. Okay, so now first I'm going to define what is an information system when in our network we only have one device. And then I'm going to define what an information system is when we have several devices. So let's focus on a network with just one device. So that will be just, it will be pictured just by a single node. On the picture there, you've got the device, there is a cell phone. And so what an information system over such a a network is, it's a collection of things I'm going to call information clusters. And these information clusters are arranged in an order. So some of them could be bigger than others. And I'm going to display them once again using arrows. But this time we can't have multiple arrows going in the same direction because one cluster is either smaller or is a part of the other, or it's not. So there are only two options. So essentially what this thing is just a pose set in sense of order theory. So it's called a partially ordered set. It's a set equipped with a binary relation that's reflexive, antisymmetric, and transitive. Let's look at an example of that. So imagine this device is a cell phone, and the information clusters. So let me remind you, these things are called information clusters. We will just refer them to clusters. So the intuition is that these clusters, they're just some pieces of information. In this example on the picture, they are approximate GPS locations of the cell phone. So we have here A, B, C, D, E, and F. And let's say the blue circles are approximate locations of the cell phone measured throughout a certain day. And let's say the orange one is the one that's measured the following day. So this would constitute an information system where you have one, let's say E, one cluster being less than the other cluster, let's say C, when that region, the region E, lies inside the region C. And so on this picture, we see that E is part of C, but then nothing else is part of anything else, except that everything is part of itself. So the idea here is to think of the information clusters as all possible informations that a device can capture. So the information system of this mobile phone is not just these few clusters, it's all possible clusters that a device can ever capture. And when we want to talk about some information that we have at hand right now, we will just isolate some clusters from that bigger set. But in general, the idea is that this pose set should consist of all possible informations that the device can capture. So that constitutes an information system over a single node. And in this case, the single node is a cell phone. Okay. Now, there are two ways of kind of interpreting what does it mean for, let's say, E to be part of C. I'd like to call it the classical interpretation and the quantum interpretation. And I apologize in advance if this terminology for quantum interpretation is not quite suitable. As far as I understand quantum mechanics, and I understand it very little at this point, it felt like a nice analogy there, which I'm going to explain now. But if you think that there is no analogy, then please do tell me so. We are talking here about possible locations of the cell phone, right? So this region E means that the cell phone is somewhere in the orange region. And we could think of this as a statement saying that the cell phone is, let's draw the orange region. Let's say this is our orange region. So the cell phone could be here, it could be here. It's an approximate location. So it could be anywhere inside this region, right? We don't know for sure exactly where it is. It could be anywhere. And so this is classical interpretation. So it's either there or there or there. And then when we have a bigger region, the region C, the options expand, right? Now, the options expand, but C actually has less information than E, because E gives us more accurately, it gives us more accurate information about where the cell phone is. So the narrower the region, the more accurate it becomes, right? So we really want to think of E being kind of almost like more than C. So the direction of this arrow is perhaps a bit opposite to what classical thinking tells us. But then there is also as I said, what I want to call quantum interpretation, where we think of this not as statement saying a cell phone is here or there or there or there, but rather we think of this as a statement saying that the cell phone is simultaneously in all of these spots. So it's a kind of superposition, right? So the statement now is that we can think of this like this. So each of these spots could be some kind of attributes that the cell phone could have. So a cell phone has this alpha attribute if cell phone's location is at alpha, but we allow cell phone to have alpha and beta attributes at the same time, even though it feels contradictory from the classical way of thinking. And if we think in these terms, then E tells me that the cell phone can have all of these attributes, but then C brings in more attributes. So in that sense, now C becomes more. So previously E gave us more information, but now C gives more information. So it's kind of dual way of thinking about this, which in one case I call classical, in the other case I call quantum interpretation. Okay, so that's as far as intuition goes for the ordering of the clusters in the information system. And we don't necessarily want to stick with one intuition. For different examples, we might want to switch between one and the other intuition. In general, abstractly, these information systems, this ordering is an abstract ordering. So we just want it to be a poset, a reflexive, antisymmetric, and transitive relation. We don't want it to be anything specific in the general theory. Okay, now the next thing I'm going to do is to define a transmission from one information system to the other. And then I'm going to use that concept to define information system over a general network. So a transmission is going to be really something very simple. If I have two information systems, what a transmission does, it simply maps information clusters from one system to the other. And it must do this in such a way that the ordering is preserved. So if one information cluster was less than the other in the source of the transmission, then when they're mapped to in the target, this relationship should remain. So it should still be less than the other. So the transmission, I mean, intuitively, this means that if I'm transmitting large amount of data, right? And then separately I transmit some part of it, then this transmitted part should still be the part of the bigger thing that I transmitted. Okay. Here is one example of that, where we could take this information system of approximate GPS locations of the cell phone, and we could have a pinned location denoted by L, and we could be measuring the distance range from the pinned location to the location of the cell phone. So we then have two devices. One is the cell phone, the other is this application that only captures distance ranges. So the information system on the right side is a bit is slightly different from the left side, right? On the right side, information clusters are constituted by intervals of real numbers, like, for example, SL interval or TM interval. And so we have a mapping. So for every circle, we'll have a corresponding interval that's given by this picture. So let's say for the C region, we will draw this line, and then we'll measure the distance from that point. I'm pointing the S point to L. So that will be my lower number, and then the higher number will be L. So that will give me the range of distance in which the cell phone is from the pinned location. So this will be an example of a transmission from one information system to another. And it's not difficult to see that it preserves the ordering. If let's say E is part of C, then the distance range for E, that interval will lie inside the distance range interval for C. So that's quite obvious, right? Okay. So we can now define what is an information system over a general network. So when we have a network, an information system over it specifies for each device, it specifies an information system there. So that pose set of information clusters with the part of relationship, right? So we can draw these kind of balloons here. And then it must also specify for each channel that there is in the network, it must specify a transmission from the corresponding information system to the other one. So from the source to the target. So for each channel here, we will have a transmission up there. And there are no further requirements. We just want that, nothing else. So for each device, we have a corresponding information system, and for each channel, we have a transmission. So intuitively, I think it's a very, very kind of intuitive thing, right? So nothing unusual about it. Huh? Okay. But we want to do a bit more than just leave it like that, because, for example, if I'm at device A and I want to transmit information to device B, I don't have a direct channel going from A to B, but I can transmit information along this path, right? And I would be interested to see, to consider that transmission. So what I want to do now is to define something that I will call composite transmission. And composite transmission will be nothing other. So composite transmission from A to B will be nothing other than, so taking all these channels that connect A with B and taking all the transmissions along each of these channels and then compose them as functions. So we basically, if we have an information cluster here, we trace it along that path. So we see where it gets transmitted there. Then we follow this path there, and then we go there, and then we eventually arrive here, and that will be my transmitted information cluster. So in the beginning, we started off down here with just a graph, a network, but now we can enrich this network with more channels, which are composites of those paths there. And so we could consider a system where we now have, as our nodes, we have still the same devices, but now as arrows, we allow all possible composite transmissions, not just the ones that come from the channels. And this way we will get a structure called a category. So what distinguishes a category from a graph is that in a category, we have a rule for composing arrows. And the rule for composing composite transmissions will just be the composition of composite transmissions by applying one function and the other. Okay. So we will call this transmission category the one where, so let me actually write this down. In a transmission category, objects are devices and morphisms are composite transmissions. I keep spelling this wrong, sorry about that. All right, so at this stage, if there are any questions, I would be very happy to take them, because what I'm going to explain next will build on this concept somehow. It will be good if we can make sure that I haven't missed explaining this concept properly.
Zurab, I don't see any questions so far in the Q&A, and nobody's raising a hand.
So, Francesco, do you think it's clear what I said so far?
Yeah, no, it's absolutely. Yeah, no, perfect. Thank you.
Okay, so what we want to do next is to consider an information.
Sorry.
Yeah, yes.
There is a question in the Q&A.
Mm-hmm.
Is the transmission category a category of other categories?
That's a very interesting question. We could think of it like that because, I mean, we could think of, instead of devices, we could think in terms of the corresponding information systems, which are just posets. And every poset is a category in its own right. So we could think of transmission category as a category of categories, except that we might end up in a situation where two devices have identical information systems. And then we do want to distinguish them as different objects because the devices are different, even though they carry the same information. So in some sense, yes. But in some sense, no, because we might have multiple copies of the same poset because of the fact that the indexing device was had just a different name. Okay, so the next thing I'm going to do is to take an information system and put some axioms on it, some requirements that it must satisfy. Now, what is interesting is that these requirements come from the part of category theory where we wanted to have a unified setting for establishing Noether's isomorphism theorems and many other similar theorems. And there's a long history behind this notion, and I'm going to touch a bit on that at the end of the talk. So we're basically taking something that seems to be like very, very kind of specialized in some sense, category theory, although maybe not so specialized because isomorphism theorems are very broad, have very broad applications. And we're going to take that context, which works for isomorphism theorems, and formulate the definition of that context basically in the language of this information system. And we're going to see that we're going to get a notion that is very natural from the point of view of the information system. And this is something that's very surprising for me, that it's because, and that's the thing that makes me hope that this notion that we're going to end up with could have applications outside mathematics, specifically to various places where information analysis comes in. Okay, so to do that, what I just said, I need two further notions. The notion of input and output. And this is going to be very similar to what this word suggests in terms of, let's say, the computer has input and output information. But even before that, I need another notion. So we will have two notions, the notion of a stash and the notion of reach. When I have a transmission from one information system to another, let's say for devices A and B, sometimes I don't want to transmit all the information, right? For example, I'm giving a talk now, and so I'm transmitting some information, but I'm not going to tell you whether I had tea or coffee this morning, unless possibly if you ask. So not all information gets transmitted, right? And we want to capture that idea. So how do we formalize the idea that some information will not get transmitted? And we will call that stash because of the meaning of this English word. Now, if we take this quantum interpretation where the smaller element in our poset, the less information it contains, the bottom element in the poset, so this is the smallest cluster, smallest information cluster, would have no information in it. So this is empty information, if you like, or maybe the least information we can get. And so if some information here from information system A got transmitted to empty information there, that probably means that it was not transmitted, right? So that's the idea of a stash. A stash is something that transmits to nothing in some sense. Huh? I mean, there is still something here, but it's the least information you can ever have in terms of the device B. So your hope that as much was concealed about this as possible. I mean, you can't conceal more than this because this is the smallest cluster on the side of B. So that's the stash. Stash is something that gets transmitted to smallest cluster. And what about reach? Maybe it's actually worth writing this down. So stash equals something that transmits to smallest cluster. And reach is simply anything that gets transmitted to. So in this drawing here, this would have been stash. And the drawing for reach will be, you just take anything on the left side, whatever it transmits to, that will be your reach. So this is reach. So the idea is that this transmission was able to reach this information in the sense that there is something that transmits to that. Something that is transmitted to. That's not a nice way of putting it. Something that is mapped to by transmission. Okay, so stash is information that gets lost. Reach is the thing that arrives in the destination. Okay, so now using these notions, we're going to define what is an input and what is an output. There are three conditions that define an input. And the conditions are written out here, and I'm going to make drawings to explain them. So let's say we have two devices, A and B. And we have a certain channel there. Let's call this channel I. This channel I will be called to be an input if it has the following three properties. So the intuition is that I is kind of A is a kind of sub-device of B through which B receives certain kind of information. And the requirement is that to express this intuition, the requirement is that if I have any information going to B, and this could be a composite transmission, it doesn't have to correspond to one of the channels. So I'm going to draw this with a dashed line. So it could have been information that comes through with a sequence of channels. And if all information that comes from here is attainable through I, so in other words, everything that's in the reach of this is also in the reach of this. So if anything that comes from here can be transmitted through I, then this transmission must pass through I. There must be another composite transmission here, so that when I compose these, I will get exactly the same transmission as this one. So it really says that anything that arrives in B and is such that I could have transmitted it, then that transmission that does work like that must be a transmission that passes through I. So that's the first condition. The second condition is that the input transmission, so the transmission corresponding to this I, must map clusters injectively. So you can't have two different pieces of information mapping to the same piece of information inside B. You don't want that because you want this I to be faithfully capturing everything. So if there are two different pieces of information in A and I is supposed to kind of be feeding into B, you want B to be able to distinguish them because A distinguishes them. So that's the second condition, that the I mapping is injective on clusters. And finally, the third condition is that if you have anything at all that's part of something that got transmitted from I, right? So I mean, think of it like this. So let's consider A to be a keyboard, right, attached to a computer B. And now computer receives certain kind of information from the keyboard. And now we take that information and we look at its part. If I'm able to consider that part inside B, then that part should have been also be possible to input using the keyboard. So if it's a word of 10 letters and I now truncate this, only look at 5 letters, then I should be able to enter those 5 letters with the same keyboard. So anything that's part of information that is in the reach of I should itself be in the reach of I. So there must be some cluster here that maps there. And I hope you will agree with me that these 3 conditions seem to be very natural ideas in terms of how the input should work for a certain device. The notion of an output is very similar. You want your output to be the thing through which information gets transmitted from your device. So input was going into B, and output will be going out of B. Let's call this O. And so the analog of the first condition is that any information that gets transmitted out from B and is kind of, we now want this condition saying that we somehow want to be able to recognize when is this information forced to be transmitted from this specific output. And the way we can say this is that whatever is non-stash of this. So remember, stash is the information that gets lost, right? So if it is true that every information that does not get lost through this also doesn't get lost through this, right? Then this transmission must pass through the output. So everything that doesn't get lost by this transmission, if it also doesn't get lost by the output, so if this output does take care of all the information that this one transmits somewhere, then this transmission must be passing through the output transmission. And then the other 2 conditions on the output are very similar to the other 2 conditions on the input. I'm not going to go into that now because a bit because of the lack of time as well. But they're written out here on the page. So we have these 2 notions, the notion of an input and the notion of an output. And the intuition behind them is that the input of your device is a channel which is a kind of sub-device of your device, which is responsible for receiving certain kind of information. And then it must be taking care of everything around that. And the output is a channel through which all the information going out from your device goes through, but not everything, only those which do not lose the information that this one doesn't lose. Okay. Now, once we have these notions of an input and an output, we can now formulate 3 conditions on an information system. And when the information system satisfies these 3 conditions, we will call it a pre-Noetherian information system. And the conditions are as follows. So the first condition says that any transmission between devices in an information system must pass through some output, some transmission, intermediate transmission, which must be an iso transmission. I'm going to explain what that means, and then some input. So this must be output, and this must be input. This must be an iso transmission, which means that the information along here must never get distorted. So it's basically a bijection in terms of the mapping that maps clusters to clusters. So if I have 3 clusters in here, and here I must also have 3, and this iso transmission must map them 1 to 1. So basically, the first axiom on the information system says that whatever transmission goes out from any kind of device to any other kind of device, there is always an output device on the source side and an input device on the target side through which this information travels. The other 2 conditions, so this is the first condition here. The other 2 conditions, these ones, they will talk about the fact that for example, the second condition says that if you've got two input transmissions, if you have two input transmissions, then the information that can be captured both by this one and that input transmission, all of that information must come from a separate input transmission. So it is kind of possible to combine two input transmissions in terms of the information that's common to both of them. And a similar condition for the output transmissions, which is the third condition here. Okay, now, believe it or not, when we have an information system satisfying these three conditions, we are very close to being able to reproduce all of these theorems of abstract algebra. We just need one little ingredient, and that little ingredient is existence of suprema and infima in the posets of information clusters, which is again a very mild requirement to put. And once we have that, we get something called a Noetherian form. So we now define a pre-Noetherian form using these three conditions, but to get a Noetherian form, we need just a bit more than that. Noetherian information system. Noetherian form is the mathematical analog of this concept, where which is slightly different from this in terms of technical detail. Okay. I want to now tell you a little bit about the mathematical examples of these Noetherian information systems. Maybe if there are any questions thus far, I'll be happy to answer them. Okay, so to zoom out a little bit, what we've done so far is we've described some organization of an information system, which enables information to travel effectively. It is constrained by some requirements related to inputs and outputs, basically. And now the question is, where can we find such information systems? And this question can be asked at two levels. First, where can we find them in mathematics? And the second is, where can we find them outside mathematics? So in terms of finding them inside mathematics, we have plenty of examples, and I'm going to show you some of them. In terms of finding them outside mathematics, this field is just beginning now, and I hope it will have a fruitful development. I see there is a question from Jeff Sanders about computability. The question says, how does computability fit, if at all? So thanks very much for that question. So I don't know too much about computability. That is one of the questions that I myself am wondering. And Jeff, if you can direct me to some literature where I can find out more, and maybe so that I can maybe answer your question to fit computability in this story, that will be great. Thank you very much. So at the end of the day, you do want this information system to serve some kind of as a computational tool, and how to set it up, that will be quite a fascinating project. Okay, so some mathematical examples. The classical example is where the devices are vector spaces. The channels between information systems are linear maps. And now the question is, what are clusters? What are information clusters? So these are subspaces. And this is not far at all from quantum mechanics, where, well, there we have a Hilbert space, of course, and the state of a physical system is captured not just as a single vector, but as an entire straight line passing through as one-dimensional subspace, right? So in quantum mechanics, you want your basic information clusters to be closed subspaces of Hilbert spaces. So this is kind of analogous to that, except now we have vector space and just a subspace. And of course, anyone who is familiar with mathematical logic will know that the idea of representing information as a substructure of your structure is a very, very old and very common thing to do. Okay, so it turns out that this system of vector spaces, linear maps, and subspaces gives you a Noetherian information system. But we have to do a bit of modification. So the modification we have to do is that, remember, we start over the channels, right? But then the composite transmissions here will actually correspond to channels because we are starting off with a category than just a graph. So we might want to identify linear maps if they act the same way on subspaces. So we will get then projective spaces as a result, not vector spaces. But with the corresponding mathematical notion of Noetherian form, we can even capture vector spaces. So from now on, I'm not going to distinguish between these two levels. So it's technical detail which that less relevant for seeing the bigger picture. So not just vector spaces. We could take all sorts of algebraic structures. We could take groups. We could take rings. We could take many other things. And that's the remarkable thing about these Noetherian information systems, that they fit all of these frameworks. And the reason why they fit is because of Noether isomorphism theorems, actually. This first condition, I mean, one of the conditions I gave, namely the one which was talking about decomposing any information in terms of output, some isotransmission and input, this is nothing other than Noether's first isomorphism theorem. And if you look at how other isomorphism theorems are proved, they often rely on the first isomorphism theorem. And so in this theory as well, the first isomorphism theorem kind of becomes the axiom, and then all other theorems are derived. But it's not the only thing. You do need a bit more than just the first isomorphism theorem, although it's the thing that's most striking, I must say. Okay, so now how far we can go? So can we really have arbitrary mathematical structures giving us always Noetherian information systems? I don't know. Probably not arbitrary, but we can go quite far. And recently, in a joint work with Francois van Niekerk, we were able to do something that initially seemed like very, very strange and unexpected. We were able to find a Noetherian information system for the category of sets. So the devices there are sets, and the channels are functions between sets, and the clusters are something very, very interesting. So they're not subsets. Subsets do not work. If I take subsets like I did with subspaces, it will not give us a Noetherian information system, although subspaces is the usual way of doing logic in mathematics. What we must take instead of subspaces is the following. So if I have a set X, then an information cluster inside the information system corresponding to this device, which is now just a set, will be something very, very interesting. And I want to slowly explain this because I would love to see a meaningful physical interpretation of this. So the information cluster here will do two things. Firstly, it will partition the set into equivalence classes. We can think of this as a kind of abstraction, right? Because, for example, imagine these dots being all living creatures, and we classify them according to the genus they belong to. If we're talking about animals, I guess. So we do some kind of abstraction. We squash things into the same group somehow. So that's what an equivalence relation does in general, right? But then there is a second thing we do after this. And the second thing is that we pick one of these classes. So we might be picking this one, or we are also allowed to pick nothing. So we first abstract, we get these equivalence classes, and then we concretize, we pick one of them. If we choose these to be information clusters and suitably define transmissions which I'm not going to do now because of lack of time, but it's all explained in detail in the blog. We will get a Noetherian information system. Now, one possible intuition for this is that imagine you have a state of a property alpha, right, that talks about elements of X. So one way of thinking of this information cluster, so in classical logic, you would want to consider the set of all the X's satisfying alpha X. So that would only give you a subset. But now what we are doing is we are specifying the set of all the X's that satisfy alpha X. But in addition to that, we're also specifying other groups of sets. And the way we can think of this is that, for example, this is the group of all the elements Y and Z, such that alpha being true for Y is equivalent to alpha being true for Z. So it's almost like saying, we know for sure alpha holds for these elements. For the others, we're not sure, but we are sure that the probability of them holding for this group is equal across the group. And there is another equal probability across another group, and so on and so forth. So it's one way we can think about this. Okay, now I am really approaching the end of the time, and I'm also approaching the end of the talk. The next section in the talk, I mean, when I wrote this, I consciously knew that I wouldn't have time to talk about this, but for completeness sake, I still wrote it up. So topological information systems is, this topologicity consideration is the thing you want to add to a pre-Noetherian form to get a Noetherian one. And in very simple terms, this is ability to have complete lattices out of your posetsets of information clusters. You don't really need complete lattices. You just need lattices, and the transmissions you need to be parts of Galois connections. But if you make them into complete lattices, then things are even easier. And there is a lot to say there. This notion comes from the notion of a topological functor in category theory, which is something that was the central concept of study under the research group of Professor Guillaume Brummer from the University of Cape Town. Okay, so I'm going to skip to that part and then come to the concluding remarks. So this notion of Noetherian information system from this talk is an adaptation of the notion of a Noetherian form that was first introduced in a paper with Amartya Goswami that's published in Advances in Mathematics. It's called Duality in Non-Nabila Algebra 4. It's a series of papers. Amartya joined in the fourth paper. The first three papers were developing background for the fourth paper, basically. The first three are co-authored with Thomas Wakefield, my former student, who is now a mathematician in America. And this paper gives all the historical background behind development of this concept of a Noetherian form, and also references. And one of the references it gives is Noether's paper, where the isomorphism theorems were first proved. Then another important reference is the paper by Saunders MacLean, where he suggested in that paper that there should be a unified categorical approach to isomorphism and other such theorems based on duality. So based on duality, that means that you want your theory to be such that when you reverse the direction of arrows, your axiom system stays the same. So it should be a self-dual theory. And that's one of the things that is fulfilled using the notion of a Noetherian form. It provides a self-dual context, just like MacLean wanted, for establishing these isomorphism theorems. And then we come to some questions in terms of useful real-life interpretations and applications. And this question of compatibility from Jeff Saunders is very interesting. And there is also one very specific question I want to end with, namely, does the category of Hilbert spaces, which is neither abelian categories, abelian categories are the first kind of nicest possible Noetherian situation, which is also very classical notion. So the category of Hilbert space is not abelian, and it's not even semi-abelian, which is a bit more general, but still a very useful notion, which captures non-abelian groups and many other structures. So in fact, the notion of a Noetherian form was in some sense developed out of the notion of a semi-abelian category. But Hilbert spaces is neither. And the question is whether Hilbert spaces also have a Noetherian form or a Noetherian information system. And if the answer to this question is yes, this could open up a way of seeing some bridge between what I've tried to present here and quantum mechanics, because the category of Hilbert spaces is what matters as far as our present knowledge of mathematics is concerned, at least for quantum mechanics. And then there is a very, very philosophical question whether the physical universe can be modeled as a Noetherian information system. So maybe some of these questions are too ambitious, but at least in the case of Hilbert spaces, it should be possible to give a yes or no answer to the question. I think this is where I'm going to stop.
Yeah, Zurab, thank you very much for a fascinating talk. And I hope you will find a few volunteers to help you address the question in blue. I would really like to know the answer. That's very nice. Thank you very much. That's really interesting. But I see, Zurab, that there are two questions in the Q&A, and maybe Ilya can guide us through them, please. And if people would like to ask a question in person, please just raise your hand and we will give you immediately the right to speak.
Okay, the first thing in Q&A is a comment from Jeff Sanders about the computability, and so he gave a reference to Dano's code. And the next is the question from the Gareth Emery. Gareth, do you want to ask your question by yourself? Yeah. You can unmute yourself.
Okay, I can speak now. Yes, thank you very much. That was fascinating. As you know from some of our earlier conversations, I'm very interested in closure in a categorical sense and its relation to self-organization. And I was wondering if, given the fact that you've had to put in infima and suprema, whether you can say anything about the closure properties of these Noetherian categories, or perhaps even pre-Noetherian categories. And then as a follow-up, if one can't do that, can one talk about the category of such categories? Thank you.
I'm a bit lost in my answer, because closure operators arise everywhere in the theory of Noetherian forms. I don't know which one to put forward. So you have suprema. I mean, for example, the standard closure operator you immediately get is that you take information cluster, you transmit, and then you can reverse transmit by Galois connection. That becomes closure. Then you can also do other kinds of closure where you take something that's not a stash of anything, and then you want to turn it universally into a stash, and that could be a closure as well. It corresponds in group theory, it corresponds to a normal closure of a subgroup. So I'm not sure if I'm answering your question well or not, but closure operators immediately come into the theory, and the theory is full of them. Maybe you want to make the question a bit more specific?
Yes. Am I muted or unmuted?
We can hear you. We can hear you.
Okay, perfect. I wasn't precise enough. I meant in the sense of monoidally closed category or Cartesian closed category.
Oh, sorry. Okay, no, I completely misunderstood your question. Okay,
yes,
so
yes. I was my bad.
So the category of vector spaces is Cartesian closed, right? We have the tensor product there.
Sure.
So with these Noetherian forms, you usually do not want even to think about products of objects. So it's a theory which, especially when you take the projective quotient, when you identify parallel maps when they act the same way on the information clusters, you don't really have these limits and colimits anymore, and you don't want to have products and nothing. So the theory in its own does not interact with Cartesian closeness at all. But you might want to make them interact and study the interactions. And this is still to come. So for example, the category of Hilbert spaces is a nice monoidal structure, which actually can be even used to describe it to some extent. There is a recent paper by Chris Hoenen, where he gives axioms for the category of Hilbert spaces. I discovered it over the weekend preparing for this talk. So this monoidal structure of the category of Hilbert spaces is quite powerful. So if one would be able to find a Noetherian form for Hilbert spaces, then one would want to study the relationship between that form and the monoidal structure of Hilbert spaces. And yeah, so things have not really been explored in that direction yet, but they're certainly worth exploring.
Brilliant, thank you.
Perhaps Jeff wants to ask a question as well.
Yeah. Here we go.
Thank you. It took me a little while to work out how to unmute. Thank you, Zurab. Lovely. In your slide that's showing, alpha is the canonical function from the X to the quotient structure. So I think you're saying clusters are formed that way from certain alphas, but there must be a condition on alpha.
We can think of clusters as a combination of a subset and a quotient set, right? Basically, it's a subquotient, but we don't have any conditions on alpha, so it could be arbitrary.
Okay, so I understand the construction. It's okay. Yeah. You choose one equivalence class.
Yeah. You either choose or you don't have to choose. And if you want to choose several, you can, but then you get a different form which is slightly less well behaved, but it's still Noetherian, even if you choose several of them, several classes. But if you choose only one class or nothing, then you get a very, very well behaved Noetherian form.
Mm-hmm. So your partially ordered sets in any of these situations actually have a lowest element because that's your vacuous information content, whatever you call it.
Yeah, exactly. They're lattices always.
Yeah.
That's
well,
the topology.
But that comes out when you said they're closed under GLB and inf.
Yeah. Mm-hmm.
Okay, thank you, Zurab.
Thank you. I really look forward to discussing Dana Scott's work. And
also, you owe me a discussion after your SAMS talk, but I never got around to emailing you.
Okay.
Thank you.
Thanks.
Hey, Zurab, can you hear me?
Yes.
I have a simple question, I think, or as I'm still trying to understand it. So how do you discriminate between two information clusters? So the way I understood it is all the elements from one gets mapped to the other one, but some of them go into like a stash. Is the difference between those two then, it's almost the things that's in a stash, you see almost the one as a subset of the other, or just in general, like, yeah, how do you tell them apart? So it's also injective, yeah.
So in the general case, you cannot like subtract one from the other. So these lattices are not closed under that operation. So I'm not sure I understand the question fully, because so you can distinguish them simply by the fact that one is less than the other, but not equal to the other. And that's how you know that they're different, but still one is part of the other. So maybe you want to make it a bit more specific what you're asking?
Yeah, I'm trying to understand that part. So maybe it is that the one is just less than the other one, but is it then that one is always kind of then a subset of the other one?
Yeah, so you can think of one being less. So for example, in this case where the clusters are equivalence classes with a chosen class, less means that the equivalence relation is finer. So for example, if I now choose another, if I make another equivalence relation where this is one class, okay, and that's the other one, this would be a bigger cluster than the previous one. So more things will be equivalent, right? Because all of these now go into one big class. But when you're describing a Noetherian system, right, you have to describe what it means for one thing to be part of the other. That should be part of giving the example, giving that information.
Yeah, no, I think I understand a little bit better. Thanks.
Thanks.
No more questions, neither arms raised.
Okay, if there are no more questions, then Zurab, thank you so much for another fascinating talk. And I'm sure we will invite you back soon because we want to know how this story develops. So thank you very much for preparing a very nice interactive talk. That was really very nice. Thank you. And before wishing everyone a good evening, please give a look in the chat. There is the link to our virtual social event. And I know that Zurab will be there because he's always there. Yeah. So take a minute out of your busy schedules to have an informal chat just now. And again, thank you very much to Ilya for the co-hosting support and for keeping an eye on the Q&A. Zurab, again, thank you so much for always being there to support us. And a good evening to all the participants, and thank you very much for following us regularly. Yeah, we will be back here next week on Monday afternoon with another interesting talk. So thank you very much, everyone, and I hope to see most of you in Kumo space just now. Thank you. Have a good afternoon. Thank you very much.
Thank you, everyone. Goodbye.
Bye.
Thank you. Bye-bye.